In problem number 5, this is a mechanisms question, and I know the answer key is there, but I'd like to go through it anyway. Whenever you're doing OChem, you always have to ask yourself, what's the driving force? So do we have an actual negative or do we have an actual positive? Now, we do have an actual positive. We have water that's acidic water. So you're going to have, some people will just simply write this as H plus, or in reality, you're never going to have individual H pluses. You're going to have water molecules. The oxygen will have 3 hydrogens positive. So the driving force here is that we have a positively charged oxygen. So what is going to happen over here? This oxygen is slightly negative, and the lone pair of electrons from here is going to get sucked in, and then these electrons from that bond are going to go onto the water, onto the oxygen to give us water as a leaving group. And we're going to have a protonated alcohol right here. Now this is equilibrium. This goes back and forth because now the water molecule could feasibly go ahead and take off one of these hydrogens and revert right back. At this point though, now as soon as we have a positively charged oxygen, this becomes a really good leaving group. And so this is going to go ahead and fall off. Again, oxygen does not like to be positive. So we're going to go ahead, and this is technically equilibrium. Going to go ahead and that's going to fall off. And now we're going to have a carbocation there. Now, I want to remind you, there is a hydrogen here. There is a hydrogen over there. So now we are going to have a carbocation right there. And this, whenever there's a carbocation, you always pause and ask yourself, what type of carbocation is it? And is there a way to make it more stable internally or intramolecularly? This is a secondary carbocation. And a secondary carbocation is not as stable as a tertiary carbocation. And what's going to happen here, before anything else intermolecular can happen, intramolecular, it's going to recognize that there's a hydrogen here, and you can actually reach over and steal the hydrogen. This is called a hydride shift. And this will happen if there's an advantage to it, and in this case there will be, because now this carbon over here is deficient. That's a carbocation. This one over here has stole the hydrogen, so that's happier. And now we have a tertiary carbocation. This is going to be more stable. At this point, we will now have water molecule come in. And there was a water molecules present at all times. Even up over here, you'd think, oh, can a water molecule go there? But again, this is a secondary carbocation, and before it's going to wait around for something on the outside intermolecularly, it's going to look intramolecularly. I should put that over here. Intra always trumps intermolecular. Now the water molecule delta minus, this is going to get sucked into here. Boom. And we're going to have an oxygen. At first, it's going to drag its 2 hydrogens with it. We're under acidic conditions, and so now another water molecule is going to come in, delta minus, pick up one of these hydrogens, dump those electrons on there. Again, this is all equilibrium, except for the hydride shift. That's not going to be equilibrium right there. But at this point here, this could fall right back off and go back to that. And now we're going to have our product like that. And there we go. I'm going to pause here.